It's your time, please.
All right. So thank you for having me. And, so I'm going to give a little talk here about derivations and, some C-star algebras and what have you. So, so let me know if you can't read what I write, and I'll reiterate, I don't have the greatest handwriting, but, I'll try my best. That said, also, I apologize in advance if any of this is too trivial for anybody. I'm basically starting then, from scratch, and so if you already know things about C-star algebra and stuff, that's terrific. I'm assuming that it's not really a deep understanding. So and hopefully, and if you don't understand it, it's too complicated, let me know and I'll elaborate on things. So kind of want to make it nice and even. All right, so before I even talk about derivations, I just want to kind of go over a little bit on what a C-star algebra is. And so I'm going to write down a couple definitions and then a very famous theorem. And we're going to look at some examples. And kind of that's the structure of this talk, is I'm going to say some definitions, maybe a theorem or two, and some examples and these kind of things, and see where we're all going with it. So I want to start off with what we call a Banach algebra. So a Banach algebra A is an associative algebra, and all that is just it's a ring with a vector space structure all added onto it. That's associative. That is complete with respect to a norm that you equip on the vector space structure. So I have some norm equipped on it. But the important thing is that it satisfies a certain submultiplicative property on the norm. So if I take two elements and multiply them, they're less or equal to the product of norms, right? So that's what we call Banach algebra. So you can certainly equip associative algebras with norms that don't have this property, and it's not a Banach algebra. So it's really that norm inequality that's an important part. The second little definition maybe is I'm going to call something an involution. Some people may call this anti-involution, depending upon the context, but I'm going to label it as a star. And it is a conjugate linear map such that, AB star is equal to BA star. And this is for any, AB in some kind of algebra, so that it can actually multiply and what have you. In particular, I'm going to equip it to a Banach algebra. It really is the main attraction. You can do it for more general scenarios, but for my purposes, it's going to be on a Banach algebra. And then finally, what a C-star algebra is, well, it's going to be a Banach algebra. That has an involution. And in particular, the involution satisfies a really remarkable property that if I take A star A and take the norm, this is the same as norm of A squared for any A in the algebra. And in fact, by having this property, you can of course deduce that the norm of A and the norm of A star are the same. Typically, the very first example, I guess, really more non-trivial first example you see of a C-star algebra is typically the bounded operators on some Hilbert space, right? This is kind of one of the canonical examples of it, and that's a non-commutative kind of aspect. And there's a famous theorem due to Gelfand and Siegel that kind of says the following, that any commutative C-star algebra, maybe I call it A or something, is isomorphic to the continuous functions on some compact Hausdorff space. And in fact, you can actually change it a little bit. And I should clarify, I mean with unit, right? So the algebra here, I'm not assuming anything about having a unit or anything like that. But if it's, when I say with commutative, I mean with a unit. And so then it's that. Otherwise, if there's no unit, it's going to be isomorphic to the continuous functions with some, C0, that vanish on the boundary of this compact Hausdorff space. And you can actually really figure out what it actually is. You can do something called the Gelfand transform, and you can figure out that this X has to be something called the max ideal space that's associated to the algebra. So they completely classified all commutative C-star algebras. So that's a good kind of classification. And the first example I want to look at is going to be a commutative one, and besides the complex numbers, which is kind of the most basic one, the other kind of classical one, at least to me anyways, is the continuous functions on the unit disk. Or it doesn't have to be unit disk, it could be kind of any arbitrary disk with radius, R or whatever you'd like, but this is going to be our unit disk in C. Right. And I'm going to think about the elements in there in polar form, kind of this RE to IX. Right? That's how I'm going to view it. So this is a nice commutative C-star algebra. You can check it satisfies all the properties. Oops. But that's not the necessarily more important aspect that I want to look at. Well, what I want to look at is I'm going to look at the continuous functions on the disk that vanish at the boundary. So it's going to be 0 on the boundary. And in fact, this is a natural subspace on the continuous functions, right? So of course the norm here equipped is the sup norm, right? That's the only norm that we're talking about here in this scenario. And in fact, it's a closed subspace, and so I can quotient by it. And in fact, if you quotient by it, a not too terrible calculation will demonstrate that this is actually isomorphic to the continuous functions on the circle. So S1 is going to be our unit circle. And it's again, I'm going to think about it in polar form, e to the ix effectively. All right. So then there's this nice kind of short exact sequence you can write down kind of from, some homology theory, that you're going to have 0, C0 of D, C of D, C of S1, and then back to 0, right? So there's a natural homology theory for this, right? Now, fine. But what else do I want to observe about this? Well, it is a commutative C-star algebra. In fact, it's actually generated by a particular element, and its adjoint, of course. But we think of it as just the element itself. Well, what is that element? Well, what I'm going to do is I'm going to view z to power n, n in z, as a basis in L2 of the unit circle or the disk. It doesn't really matter, right? Because they're all isomorphic. It's actually, isometric isomorphic. But the point is that I want to view these elements in L2, and I can kind of naturally embed, this C of D inside of, well, L2 of D, if you want to be a little more precise. And then I want to consider the following map: U acting on L2 of S to itself via U on a Z to power N is just Z to power N plus 1. So it's a shift. It's really just a shift. And it will have the property that U star U equal U star is 1. And in fact, you can show that everything is going to be commutative, obviously, because we're only dealing with these kind of, if you like, Fourier series, right? But the important aspect is that this shift, you can compute its spectrum, and you're going to get back precisely D, the disk. So kind of what I'm driving at a little bit is that one hand, this algebra has this short exact sequence. There is a shift that actually has spectrum D, and you can actually show this A is actually a C-star algebra generated by this U, right? Powers, kind of series form and all this kind of stuff with all the things attached to it. And so, and the reason why I want to think about that is because this is a good way to view what we call the classical or commutative disk, because what we're doing is we're associating this particular compact set, right? Because of the fact of the Gelfand-Siegel theorem, that yes, of course, it's functions and things like this, but I want to view it as a topological space, and so we typically view this algebra as the classical or commutative disk, right? Okay, so this is a good starting example. And the next example I want to talk about is a very well-known one called the Toeplitz algebra. And the Toeplitz algebra, well, we're going to make some observations about it. So I want to do a little setup for it. So there's many ways to discuss the Toeplitz algebra and how it's created. In fact, it's a very famous result due to Colburn's theorem that there's a universal way of representing this, right? And that's not so important for what I want to talk about, but my point being is there's many ways to achieve this algebra. So I'm going to let H2 of D be the Hardy space, and I'm going to view it in the sense of that I'm going to write power series so that the the squares of the coefficients converge, right? So instead of, you can write with integral representation, but I want to view it as a power series way, right? And this is well known to be a Hilbert space and what have you. And so I'm going to take f of z maybe to be my summation, and it goes from 0 or 1 or whatever to infinity e sub n, z to power n. And that's going to belong to my Hardy space. And the z to power n is going to represent my basis again in H2. Right? So by abusing notation, I'm going to have z to power n be the basis again, but it's going to be only greater or equal 0 is the key observation. Right? And I'm going to define another map. And again, I'm going to use U for, it is an abusive notation, but there's a reason why I want to use the same notation that maps the Hardy space to itself. Via, well, U on an F is going to be just multiplication by Z. Right? And, on the basis, it's a shift again, but there's a key observation that's different. So the big difference is that while UU star will be 1, U star U will be 1, UU star is not 1. In fact, it's 1 minus a particular projection. So right off the bat, these two things aren't going to commute. And so what we're going to do is we're going to define fancy T or something to be the C-star algebra generated by this U now. All right, so we can typically call this thing the unilateral shift versus over here, the shift worked in both directions because I was allowing, my indexing going to Z. So really the U star U being 1 and U star, really this tells you that the star is the inverse to it, right? Unlike here, it's not, right? And so there are other ways, like I said, to represent the so-called Toeplitz algebra. I guess there's a cross product way to represent it. Again, there's some sort of universal representation for it, but none of that we're going to worry too much about. Right? And like I said, this guy's called the Toeplitz algebra. Right. Now, what do I want to know about this guy? Well, as an operator, this U, you can compute its spectrum, and it turns out that it's also the disk again, the unit disk. Fine. What other kind of little observations can I make? Well, if I let fancy K be the ideal of compact operators, in L2, or sorry, yeah, H2, it doesn't matter, right? Then it can be shown that K is actually equal to the commutator ideal of the Toeplitz algebra, meaning that I look at the commutator of U and U star and generate all the formal elements of that guy. All right, so this actually turns out to be this compact operators. So you can kind of view the compact operators sitting inside this algebra. Okay, well, it is an ideal, right? And so I can quotient by ideals. And so it's natural to consider T quotient K. Very much like how we are naturally considering this quotient, right? Except here is a little bit easier. I want to figure out what in the world I can identify this with, right? But we need some more help to do this. And so the way to do this is kind of the following way. So we're going to first identify the Hardy space with the subspace in L2 of S1 spanned by, well, e to I n x, n is bigger or equal 0. Right? So remember, I'm thinking of the elements on the circle as e to ix, right? And I'm going to let m sub f be the multiplication operator by f, right? And then finally, I'm also going to let P be the following projection. So it's NL2 to H2, and it's going to be the orthogonal projection onto the span of this thing. Okay. Okay. And with that, I can finally define what I'm going to call a Toeplitz map or Toeplitz operator. And it's precisely a map, T sub f, that takes the H2 back to itself by Tn and f. What I'm first going to do, well, I'm going to multiply by f, so I'm going to do this multiplication operator, so fine. But then I need to make sure I land back inside the Toeplitz space. So I'm going to project. Right, because by multiplication by an f, and I should clarify, this is gonna be a continuous f. It may spit me back in just to L2. I may not be back in this Hardy space in general, so I'll have to project back to it. Right, and this guy is we're gonna call a Toeplitz map or Toeplitz operator, whatever you'd like to call it. Right. Okay, now. Once I have this in place, I can finally define something that will map this to a well-known algebra. So finally, we can define a map I'm going to call alpha that will take the continuous functions on the circle precisely to here. This quotient. And how I'm going to do that? Well, I'm going to take my function f from the continuous functions and just go to the class of the Toeplitz operators. Right. Oops. So fine, that's great and dandy, but I want to know something about this map alpha. And in fact, what you can actually do is show it's actually an isomorphism. So turns out this alpha is an isomorphism. So what we really have, we have now this being an isomorphism to C of S1, but we can create a short exact sequence again. right? So I'm going to have my ideal of compacts sitting inside my templates algebra, which when I look at my quotient through the homology, it's going to be C of S1. And if I pair it with this spectrum of U being the D, I've got a very, very similar structure to what I had over here, right? Here's my short exact sequence. Here's my my spectrum. So we typically can view what is called the templates algebra as the non-commutative disk, mainly because of the fact that, one, the spectrum of this generating element gives me the whole disk, and the quotient is precisely C of S1. And so we're trying to kind of visualize, you know, a non-commutative version of the Gelfand-Siegel theorem, which, you know, there is none, but you know, it kind of trying to this notion of identifying, you know, this space with the compact Hausdorff space. It's max ideal space. And so this is kind of why we kind of refer to this as the non-commutative disk, right? All right. And so you can create all sorts of interesting other non-commutative objects, which kind of spawns this notion of non-commutative geometry and such. Okay, so with that in mind, I want to talk a little bit about some derivations, and particularly the derivations on algebras, and then specifically, you know, the ones that I have in my two examples here. So let's go back to some basic definitions and see what we can say. Okay. So let's let A be a Banach algebra again. And script A is going to be a dense subalgebra of A. All right. A linear map, D, taking my script A to A, is called a derivation if it satisfies the Leibniz rule. In other words, D on an AB equals A D on B, plus, I guess the other way around, D on an A B for any A and B in my dense domain. So with this definition, I allow for things to be unbounded. If it turns out that your dense subalgebra is the whole thing, then this would be a bounded derivation. And then, you know, any other kind of proper subspace or subalgebra, right, this will be typically an unbounded derivation, right? So this definition incorporates both of them. If A is a star algebra, so it has a star on it, and this guy is a dense star subalgebra, then if I have the requirement that D on an A star is D on an A and then take the star, we call this a star derivation. Right. Okay. And then with the last example for a little while, our definition for a little while, is the following. So I'm going to let, again, A be a Banach algebra. And my script A be a dense subalgebra, but it's going to be a proper. Right. And D will take script A to A, be a derivation. So then we say D is closed if given an AN and A in my dense subalgebra, so that the sequence AN converges to A, and D on an AN converges to some B, then it must follow D on an A equal B. This is what we call closed. Very, very similar to, of course, what you would call closed operator, right? I need to discuss unbounded operators. And similarly, it's closable if A n goes to 0 and you know, D on A and going to B, implying B equals 0, we call closable. So this guy is called closable if, you know, same thing here, but now my A n goes to 0, this still goes to B, and this will imply B equals 0. Right? So, you know, it's just basically, you know, the same kind of definition you would do for unbounded operators. Okay, so now I want to look at a couple of examples of some derivations. So I'm going to let A be any Banach algebra. And I'm going to consider D taking A to itself, so the domain is going to be everything, via D on an A is going to be a commutator B with A for some fixed B in A. So this is a bounded derivation, right? In fact, you can show the norm is less or equal than twice the norm of A times B, right? So the commutator, of course, is, you know, very well-known example to satisfy Leibniz rule, right? You might show this in abstract algebra class or something. But yeah, it is a very, you know, a very nice bounded derivation. Great. What else can we talk about? Well, my example 4 is I'm going to let A be the continuous functions on the unit circle. And script A is going to be the trig polynomials on 0 to 2 pi. So I'll exclude the 2 pi. So again, I'm viewing the elements on the circle as e to ix, and x is going to go from 0 to 2 pi, and just, you know, we'll throw out this end for it. And then I'm going to define a D taking script A to A via D on an A, and I'm going to evaluate it at an x, so I can write it down, is going to be 1 over I d dx of A of x. This is an example of an unbounded star derivation that's closable. Right? It's triviality to see that this is, of course, a derivation because of the fact that it's the differentiation, which we know, you know, satisfies Leibniz rule, right? But and then, you know, if you think about from functional analysis courses, right, this is one of the most, you know, the derivative is one of the, you know, go-to examples for unbounded things, right? And so, you know, the same kind of idea, and that it's closable with, you know, particular domains. And then to make it a star derivation, this is why we have the 1 over I. You could have equivalently put minus I as well, and that's to, you know, satisfy the star relation here, right? Okay. So what other example do we have? Well, so my final example for now is I'm going to let H be any separable Hilbert space. Another reason I'm really doing that is so that I can write down a countable basis. It's not completely necessary, but it makes things a little bit easier. And I'm going to have countable basis EK, k greater or equals 0. Right? And I'm going to define, well, a U taking H to itself via, well, if I'm calling it U, then I'm probably going to be doing a shift. So a unilateral shift. And I'm going to let A be the C-star algebra generated by U, and, you know, this is really the Toeplitz algebra. just writing it in another way, and that's the remarkable thing that it's got this universal classification. And I'm going to define something called the label operator. So blackboard K on an EK is just going to be KEK. So it labels where I'm at in the sequence, right? And it puts that factor up front. This guy is an unbounded self-adjoint operator on H or in H or however you want to phrase it, right? Okay. So with that in mind, what I'm going to do is I'm going to let script A be the polynomials in U and U star. And I'm going to consider D sub blackboard K on an A. Well, it's going to take script A to A, and it's going to be via the following way. D script K on an A is going to be the commutator of K with A for any A in script A. So this is going to be an unbounded derivation. Okay, so we've got a lot of examples here, a lot of nice ones. We've got, okay, the commutator, fine, that at least in, it's always bounded there. The derivative, which is a very famous one, and this kind of one that's a commutator with something unbounded, and then it stays unbounded. Okay, now here's a nice little fact due to Sakai from, I believe it was in the 80s. This is due to Sakai. And what he showed was any bounded derivation, D, on a Banach algebra, A, must be of the form, well, D on an A must be a commutator of X with A, where X is in the weak closure of A. And in the case of this C-star algebra that's generated by this shift, this unilateral shift, it's actually the essential commutant. And in that particular scenario, that's not a very well understood space, right? But what it really says is that, any bounded derivation, this is the only way you can classify it. It's got to be a commutator, right? And so, in fact, what this actually tells you in commutative C-star algebras, there are no non-trivial bounded derivations, right? Because it would have to be a commutator. And of course, if it's commutative, the commutator would be 0, right? So, in kind of all classical or commutative C-star algebras, there are no bounded derivations that aren't trivial, right? So there are no non-trivial bounded derivations on a commutative C-star algebra. And so, like I said, this was done back in the 80s. So you kind of say, okay, well, they've been completely classified there at this point for that, right? So maybe it only makes sense to study things, bounded derivations only in non-commutative C-star algebras or what have you, or non-commutative Banach algebras. And that's true, but it doesn't discredit the fact that the derivative is still a good, honest derivation. It's just unbounded, right? And so you have to allow that into your mix if you want to talk about derivations in general. And in fact, it can be shown, at least on C of S1, that any unbounded derivation, or any really derivation, that's, because the bounded ones are trivial. So any derivation is of the form f of x times 1 over I ddx for f being continuous on the circle. So it must be of the form basically differentiation up to some multiplication of a continuous function. Right, so you can show this, and it's not too terrible to demonstrate. Right, so that kind of completely classifies all the derivations, the non-trivial ones on the continuous functions on the circle. And you can do the same for the ones on the disk and so on in this kind of fashion. So the question now is that, so this classifies kind of all the derivations on the commutative disk, if you will. So how would you do this on the non-commutative disk, right? And to do that, we need a little bit more setup, right? So we need a little bit more setup. So I'm going to need a little definition. So again, A is a Banach algebra. And script A is a dense subalgebra. Right. We call a derivation D, taking script A to A, approximately inner. If there exists a sequence AN from A, so that D on A is equal to a limit as n goes to infinity of the commutator of AN with A for every A in the domain, this script A. Right. Incidentally, this guy cannot be approximately inner, right? Because if it were, it'd have to be a limit of a commutator, which they'd all be 0. So this is not possible to be approximately inner. So there are derivations that are not approximately inner, right? And even in here, neither is this, and it's a commutator. So and we say in, you know, so there's another notion of saying a derivation's inner if it's just a straight commutator. But the problem is that this is of course not an element in the algebra A, right? So this is neither inner nor approximately inner or any of that. So there are these derivations that are out there that are not approximately inner, or inner in themselves, right? So fine. But again, you know, we kind of want to study, you know, derivations on this Toeplitz algebra, or however you want to write it, right? In other words, I want to study D taking script A to this T with this script A, the same exact domain here, polynomials in U and U star. Which, by the way, that maybe you want to change your domain too, right? It's this particular domain. This is being very modest, right? I'm taking this the polynomials, a small domain. You may want to say, maybe I want a bigger domain, right? Right. So kind of you can kind of think of this as a small domain and a big range, but maybe I want to make the domain larger and the range smaller, right? So you can play around with these things and you may get different aspects. That's actually something in other work that I've done as well, right? So I guess I should, at this point, I should maybe clarify that this classification on these derivations on these non-commutative things, this is all work that I've done. Most of these other things are well understood things, right? So, but this is where kind of my contribution has kind of came in, right? So let's try and figure out what this could be. Unfortunately, we need some more help, right? We can't just write down anything at the moment. There are other little key aspects that we need to be able to do this, right? As it usually goes. So one thing I want to observe first of all, so we need some help here. So here's some things I want to observe. Well, let's look at the script A, right? So it's these polynomials in U and U star. And let's go back to wherever I wrote it, right? We have this alpha map that's an isomorphism between the Toeplitz quotient of the compacts via the classes, right? So it stands to reason that the class of this script A is precisely the trig polynomials on in or on C of S1 for the very reason of this alpha map, right? And so fine, right? So the class of S is this. So why is that important? Well, we have a little lemma that says that if you take D from script A to this Toeplitz algebra, is any derivation, then D, when I look at script A and I restrict to the compacts in there, will map precisely to the compacts. And so incidentally, so this D actually defines on equivalence classes another derivation. And just for lack of notation, I'm just going to call it the class of D, right? You can write another notation, of course, but just so there's not too much notation floating around, right? So any derivation on this with this polynomial domain will define one of the equivalence classes, which happens to be the trig polynomials, and we know how to precisely right, with this polynomial trig polynomial domain, this is all of them, right? So that means for any derivation D, on here with this domain, the class of D has to be of the form, 1 over I f of x d dx, for f continuous. And in fact, I'm going to write it in a theorem just so that I can do some labeling a little bit for the later thing that I want to write down. So there's a little theorem. Well, actually, I should clarify what I'm going to say. So this tells you that it's on classes, but actually you can say more. That if you have a continuous function on the circle, so it's not even just that if I have a derivation, I can create a class. What it actually tells me the following. So let f be a continuous function. It actually goes the other way around. There exists a derivation, d sub f, taking this script A to the Toeplitz, so that the class of this df is precisely this thing. Right? So given any f, you can always find a derivation that will have this property. Now, the real question remains is, what is this d of f? So once you take out the compacts and quotient by it, you can get this, that this is what it has to be. Right? And it's not too terrible to do. But this actually is rather important, because what it's going to tell us partially is that, well, when I'm going to try and classify derivations, kind of the idea of what to do to see how this is going to work is that you say, okay, I want to consider derivations that are so-called invariant and others that are so-called n-covariant, where n is not 0 or whatever. And really what this refers to is that you can create an automorphism group on the Toeplitz algebra, where effectively that if you apply this automorphism to u, you get e to the I x or theta or whatever, u and 0 on the diagonal terms in this algebra. I'm not writing the terms explicitly out as some series, just to keep it down a little bit. But the point is that it would be invariant if the automorphism of the derivation just gets you back to derivation, and call it n-covariant if you when you apply the automorphism, you're going to get a phase factor out of this somehow. And you can also show that derivations are, that there are going to be some kind of Cesaro sum of these n covariant derivations plus the invariant, and this is the only way to decompose them in these kind of domains. Now, of course, if you have better domains, it may not be a Cesaro sum of them; it might be an actual norm convergent sum. This depends on the situation you're in. But at least in this scenario, it's a Cesaro mean one. But regardless, that's getting a little too much into the actual details about it, which is not really the point of the talk, but it gives an idea of what I'm about to write down of how you would go about doing this. So I'm going to let D be any derivation with that domain. Then there exists a unique continuous function on the circle so that D decomposes into the following thing. D sub f, where it's precisely this D sub f, plus some D tilde, where D tilde is approximately inner. So all derivations on the templates algebra with this small domain decompose precisely to something approximately inner plus a special type of derivation that has this property that if you take its class, you get the derivative, which is pretty phenomenal. Now, you can actually figure out what this D sub f is, and I'll give you a little idea of what it is. There's a version of a templates map involved with it. It's a complicated looking formula, but you know, you can show that this D sub f on an A kind of looks like, and you know, it's not equal and it's not approximate, but you know, looks like maybe I put in parentheses. But it's going to be some f of u, some function on u, namely this function, opposed to f of x. And you're going to get the label operator k with an a in a commutator for every a and a. It's not really this precisely, but it's pretty darn close. But it looks very much like, you know, this DDX thing, right? Because you can kind of think of the label operator as, you know, if you apply it to a u to power n, you get a factor of n out. So it looks kind of like a differentiation on an exponential, effectively. And in fact, actually, if f equal 1, then this is precisely the commutator of k with a. So for a very specific f, it will be the commutator of this very special one that I wrote down here, right? So so this is kind of the thing with that, right? And before I mention maybe a little bit briefly on spectral triples, I want to say too is that, you know, we've studied these as well on things called Bunce-Dedens algebras and Bunce-Dedens templates algebras and such, and you get similar decompositions. And with the Bunce-Dedens, because you can associate this with supernatural numbers or what have you, depending upon if that's infinite or not, the decomposition changes a little bit. But it's of this kind of approximate inner plus something special. And if you change the domains, this is also something we've also considered. A bigger domain, maybe you want to have, you know, smooth subalgebras, very much akin to, you know, the infinitely differentiable functions, right, inside of C of S1. Well, what changes is not that special derivation so much more as that D tilde is no longer approximately inner, but it'll be flat out honest inner. So changing the domains will change these things a little bit. And then again, it's also adjusting the range too. So it's not just going to be to in this case, the templates or the continuous functions. It's going to not only stay, it's going to stay in the same, you know, the range will be the domain as well. So kind of, you know, changing these things up a little bit. All right. Okay, so, well, I guess with this spectral triple section, so I guess the whole, one of the points of, besides this, the classification things, which in its own right is a great thing, but what's a good application about these kind of things? And this has to do with spectral triples. So just quickly, a spectral triple is a triple, script A, so not the same script A here or anything like that, H and a D, so new symbols. H is a Hilbert space. Script A is a dense subalgebra. Star subalgebra, sorry, dense star subalgebra. And A is a C-star algebra that acts by bounded operators on H, meaning there's a representation that, you know, if and you know, I guess I'll write out, you know, so there's exists a representation pi A to B of H right? So that pi and an A is a bounded operator, right? So the most common way to think about it is if you have a C-star algebra, you can look at the so-called Gelfand-Neymark-Siegel construction to make a Hilbert space, and then you get a natural representation out of that. So that's kind of one of the go-to examples in that scenario. And this D is an unbounded. It doesn't have to be self-adjoint, but for the time being, I'm going to say it's self-adjoint. But it doesn't need to be. But it's an unbounded operator that's self-adjoint in H, so that the commutator of D with a pi on A is bounded for any A in this dense subalgebra, and 1 plus D squared to power minus 1/2 is compact. Now, if D is not self-adjoint, you're going to have 1 plus D star D to negative 1/2 and 1 plus DD star to negative 1/2 be compact. That's the only real difference. But like I said, it need not be self-adjoint. This is just the kind of the go-to thing. And so really the idea of what to do, and I'll just kind of explain in words since I'm almost out of time. But the thing is that derivations can lead potentially to spectral triples, because you can create this D through what's called an implementation of the derivation. So there's a way to associate the D with the big D with those little D's, and it turns out if you implement it in a particular way, this commutator is really going to then end up being a pi on the D. Is kind of the little D is how it will work, and so it gives you a natural way of controlling that. And so in the classical sense with this C of S1, using this little d to create the unbounded operator D in the implementation, it creates an actual honest to goodness spectral triple. And it's a very classical result. And it's a very well understood example. So you might say, okay, well, let's try this with non-commutative scenarios. Well, it turns out with this derivation where I've created this particular domain and I try to implement it, no matter how hard you try, you're never going to be able to construct a D that will satisfy all these properties. It's impossible. So there are no non-trivial spectral triples on the non-commutative disk where it's been implemented from this little D. So and that's kind of unfortunate, because you would expect that, you know, the Toeplitz algebra, it has a lot of nice properties, especially with K theory and all these kind of things, and you would expect to be able to find some non-trivial spectral triples this way, and it's just a no-go. And it also happens with the non-commutative annulus as well. So that actually makes you really think that maybe those domains are just not good. So maybe allow a larger domain and a smaller range to see if you can control it that way. And in fact, in the Bunce-Dedens algebra, this actually has led to some spectral triples, and some of the work that I'm currently doing and it's in the process of kind of, you know, finishing up the paper or whatever, and then looking at Bunce-Dedens Toeplitz in the next go hand. So and it comes down to changing the domains, but it becomes a lot trickier because, you know, this is such a nice domain and it's relatively easy to work with when you allow this larger one that you want it to look like the infinitely differentiable functions in a non-commutative sense. So now you got to start putting different type of topology on there, and really it's going to be looking at Fréchet spaces and these kind of things, and it gets a little more complicated. So I guess I will stop there.
But excuse me, so you still have a lot of material?
What's that?
I would suggest to stop, you know, the talking about, you know, a couple of minutes. How about that?
Oh no, I mean I'm fine. I mean anything I was going to write down, it will take too long to write down in a couple of minutes. So yeah, unfortunately.
Time for questions and answers, so it's almost an hour.
So yeah, so any questions then?
No, did you finish?
Yeah. The next little thing will take too long to write down, I guess, is the point.
Yeah.
So it basically it's just going to reiterate what I just kind of explained a little bit in words with the spectral triple thing, and it's you know it's so yeah. So I guess and then any questions?
Yeah. So do you have any questions for our speaker? it seems
I have a
okay. Please.
I have a question about.
Mhm.
So you characterize the derivation on template algebra,
Mhm.
and how about so next stage is so C-star cross product. How about do you think about the classification of derivation of cross product by of template algebra by finite group or discrete group or something?
Not quite, not at the moment, but it's definitely something I've thought about. And kind of the underlying thought of this is more so with the Bunstedin's algebra, in particular
Yes.
when the supernatural number is finite. So then you're going to get this kind of this kind of discrete, and then you'll end up with, of course, the matrices with particular things on there as well. So there's some of that. That's in a paper we wrote a couple years ago of classifying the derivations on Bunstedin's in general, and that part there. But in general, not so much yet. But it's definitely something that kind of see to probably happen in the future for sure. We just kind of see what we can work with these well-known things, and then see what kind of classifications can happen and make these spectral triples. Right. That's kind of the overarching goal at the end. A little bit look at the K theory and these things. So
I see. Thank you.
Mhm.
Is there anything else for our speaker? I have a quick question because
Yeah.
Is there any realization of the theory of derivative for matrix algebra? I mean, like specific on matrix algebra. So,
Is there a notion of to make a derivative on a matrix algebra?
yes.
I mean, I don't know. I mean, I guess the closest thing would be well, I guess this would be, that's a good question. I'm not really sure. I'd have to think about that actually. Yeah, I'm not really sure.
Okay.
I'd have to think about that.
Because matrix algebra is kind of, it's not abstract. It's
right.
very concrete object. And then, with matrix algebra, maybe you can find some applications, but I'm not sure about that. It's just curious.
Yeah, I don't know. I mean, it's very concrete. So you probably could sit and work out the details of just start with the derivation and start playing around, and then decide which you want your domain to be and all these things like this. But yeah, I'm not sure. I guess I haven't thought too much about that. So.
So, did you see any applications of this theory in quantum information?
Oh no, no. This is this kind of this is very much there's really no application in sight outside of the spectral triple or computing K groups and K theory and these things. I don't really know of actual real applications as far as other than I compute some more abstract stuff. So no, I'm not sure.
I think maybe Hiroyuki knows because he also studied quantum information and this stuff.
Yeah, I don't know. Maybe 100 years from now, maybe somebody will find an actual application to what this could possibly do outside of more math. I don't know.
I think it would be very nice if there's some kind of concrete computation or structure for matrix algebra.
Sure.
I think it would be very nice.
Oh, of course.
All right. Yeah. So if we don't have anything else for our speaker, I would like to thank the speaker for his interesting talk, and thank you everyone for being here today. So we this is just very first talk in this season, and we have 10 talks, right? So next week we have another talk from Hungary on matrix analysis, and some kind of maybe some aspect in quantum information. So I hope to see you next week too.
Thank you, Matt, for a great talk.
Oh yeah, no, thank you. Hopefully it was enjoyable.
Thank you.